Hey guys, so we were looking before at specific heat capacity and changes in enthalpy, and now we'll be using that to look at the chemical changes in chemical reactions, or the energy changes in chemical reactions. So really what we're looking at is what we have the reactants, what we're putting some energy in to get a transition, to bump over the transition state to get the chemical reaction going, and then what happens to the products, is there a change in energy levels? So would it be that it releases heat or absorbs heat? So burning a piece of wood demonstrates that energy changes accompany chemical reactions. So when we burn the piece of wood, the chemical reaction is the combustion. But we know that energy changes occur because we feel heat and we see light. So energy is released in the form of heat and light. So some of this is heat into the surroundings, so that's why the air around it feels hot. And some is released as light, so that's why we can make a campfire at night and then we can still see each other in the dark. Substances that react to produce large quantities of heat are also known as fuels, because a fuel really is something that we use to give us energy. So petrol, we burn petrol because it gives us energy to move our car. So wood, coal, oil, kerosene and natural gas are all produced as all fuels because they produce useful quantities of energy. So that means large amounts. There's no point in having a fuel if it doesn't give you enough energy for its weight. So for heating purposes, they react with oxygen in the air. Release of energy in a chemical reaction occurs when the reactants have a higher chemical energy than the products. So that means the reactants there have a higher amount of energy than the products here. So there's a change in what's going on with the chemical reaction. Chemical energy of a substance is a type of potential energy. So chemical energy is that all the molecules are sticking together like normal. Then when we break the bonds, we're getting a release of energy. So this is the chemicals storing potential energy. So stored chemical potential energy is called the enthalpy of the substance. A collection of atoms or molecules that is involved in a chemical reaction is called a system. So this is what's involved. Anything around it is called the surroundings, and that's what we're going to be measuring to say if there's a change in heat or if there's light being emitted or energy that's being released into the surroundings. So an example is a flask with a substance in it, what we're looking at here. So we're looking at systems and surroundings in this case. So the surroundings is the flask, the outside of the flask, and the substances in contact with the outside of the flask, so whatever's in the box here. And the system is all the things in green, so it's the inside of the flask and the contents of it. If a reaction is carried out in solution, then the species involved in the reaction is in the system. So all the molecules and ions and things like that that are involved in the chemical reaction are in the system. But the solvent is part of the surrounding. So all the water molecules surrounding it that are not partaking in the reaction are considered the surroundings. In a gaseous reaction, the reacting molecules is the system, and all the surrounding gases that are not part of it are part of the surroundings. So enthalpy, if the enthalpy decreases during a chemical reaction, the energy must be released to the surroundings. Because remember when we said if delta H was negative, so it means it's an exothermic reaction. That means exothermic means energy is being released into the surroundings, usually as heat. So what we see is that we have reactants and the products are less. So this change here is the amount of energy that's released into the surroundings. So what I usually think of is that the reactants have a certain amount of energy. We break all the bonds and form the products, and therefore the products have a less amount of energy. So what happened to it? It went from high to low, and therefore it has been pumped out of the system. And that's why when we have exothermic reactions, they're negative, because there's a change from high to low. So enthalpy difference between the reactants and products is equal to the amount of energy released to the surroundings, because we can't make energy disappear. So energy from the system has been lost to the surroundings, like blowing air out of you. So in this case, it's an exothermic reaction because energy was released into the surroundings. Enthalpy is stored in chemical. If the enthalpy of all stored energy is lower than the products for the reactants, then it's an exothermic reaction. So combustion reactions release heat and light energy. In endothermic reactions, so that's the opposite. So endothermic means that we're taking energy from the outside in, and that's why the solution will feel cold if it's an endothermic reaction. The products have a greater enthalpy than the reactants, so it's the opposite of what's happening. So we have a certain amount of reactants, we break all the bonds, and then we form the bonds of the products, and those products have a higher stored energy than the reactants. So this change is positive, and therefore we're pulling energy from the outside in, and therefore it's an endothermic reaction. So enthalpy difference between the reactants and the products is equal to the amount of energy absorbed from the surroundings. Because we're absorbing the heat from the outside, it's making the outside feel cold, it's endothermic. So the enthalpy of the products is greater than that of the reactants. Various forms of energy to be involved in endothermic reactions are such as carbon with sulfur to produce carbon disulfide, and this absorbs heat energy. So if it absorbs heat energy, it means it's endothermic. Photosynthesis absorbs light energy. So the plants absorb light energy to form sugars, and then the sugars are stored energy. So therefore, it's an endothermic reaction. It's using the light from outside to using the chemical reaction. Recharging a car battery, chemical reactions are also pulling in energy, so they're endothermic, because they're using electrical energy from the outside and putting it into the system. So endothermic reactions absorb energy from the surroundings, causing it to feel like it's cooling down. However, exothermic reactions release energy to the surroundings, and therefore it feels like it's hot. So when we measure the solution in an endothermic reaction, we're going to have a decrease in temperature. But exothermic, because we all know that combustion or burning things releases heat, therefore it heats up the surroundings, and therefore temperature rises. So the delta H values are negative for exothermic reactions and positive for endothermic reactions, because remember I said that reactants were high energy and then they go to low, and therefore this change is releasing the energy, and we get a negative change, and therefore it's exothermic. But the opposite is occurring in endothermic. So the reactants are low, the products are high energy, and we're pulling in energy to get to this high point, and therefore it's positive change, but it's pulling in energy, making it feel like it's cold. So in exothermic reactions, the final enthalpy is less than the initial enthalpy. So delta H is negative. We're losing enthalpy in the system, and therefore we're losing energy to the surroundings, making it feel like it's hot. In endothermic reactions, the final enthalpy is greater than the initial enthalpy, and the delta H is positive. So to gain in enthalpy, the system is pulling in the heat from outside, and the transfer of energies from the surroundings into the system. So pulling it out to in. So delta H is really the heat of reaction, and it's equal to the heat of products minus the heat of the reactants. So the enthalpy H. So heat of reaction is equal to enthalpy of the products minus the enthalpy of the reactants. So it's also known as the heat of reaction, and it's denoted by delta H. This indicates a change of enthalpy in the system, and surroundings must undergo an equal but opposite change experienced to that by the system, because remember, energy is not lost. If the system requires energy from outside, it's pulling in energy, and therefore the outside is losing energy, and therefore it feels cold, and the opposite's occurring in exothermic reactions. So the values of heat of reaction are usually given in per mole of one of the reactants or products, because in chemistry we use the unit moles, and this usually gives us a more accurate and very specific amount of heat per mole. Therefore we can say instead of 2 moles we have 1 mole, and it will be the same ratios, and we can then compare and contrast. So here today we were looking at exothermic and endothermic reactions. So just remember that exothermic reactions, the products have a lower amount of energy, so therefore it's releasing heat, and the delta H is negative. But in endothermic reactions, the delta H is positive because it's pulling in energy and making the reactants higher than the products higher than the reactants. So using that, we can just quickly answer some questions. One of them is question 6. The reaction below is exothermic. So we need to make sure, remember, exothermic means heat is being pushed out into the system, into the surroundings. Which of the following is correct? Enthalpy of S is smaller than SO2. If this is an exothermic reaction, the reactants have more energy than the products formed. So S is smaller than O, so it's not this case. The enthalpy of O, oxygen, is smaller than SO2. So in exothermic reactions, the reactants have more energy than the products formed. So it has to be greater, and it's not this one. The heat will be absorbed. It says it's exothermic, so that means it's going to put heat out into the system and feel hot. So exothermic heat is not absorbed, it's released. So the enthalpy of SO2 is smaller than that of S and O2. This is true because exothermic reactions, the products have less energy than the reactants, and this is what it says. SO2 is greater than S and O2 together. So that one's right. Question 7, the reaction below is exothermic again. Which of the following is incorrect? So we're looking for the false one this time. The delta H value is negative. This is true because remember we said that delta H is negative for exothermic reactions and energy is released into the surroundings. Enthalpy of nitrogen or N2 is higher than NH3 or ammonia. It's true because exothermic reactions have the reactants have more energy than the products. So the reactants here, N2 and the hydrogen, and therefore it's higher than this one. So that's not the one. C, heat will be released. It's true, it says it's exothermic, so therefore it's giving heat out to the surroundings. So heat's released. D, enthalpy of the hydrogen is smaller than the enthalpy of the ammonia. It's false. Exothermic reactions, the reactants have more energy than the products. So this one is the correct answer to pick. Question 8, the reaction below is endothermic. So remember that's pulling in energy and therefore it's feeling cold. Which of the following is correct? CO2 has a lower enthalpy than calcium carbonate. In an endothermic process, the products have higher energy than reactions, so the CO2 here should be higher, not lower. So it's not this one. Heat is released, it's not. It's being absorbed in endothermic reactions, so it's not C. Calcium oxide has a lower enthalpy than calcium carbonate. Again, in endothermic processes, products have a higher energy than reactants. So this one, the CaO, should have a higher enthalpy, so it's not this one. The delta H value is positive for B. This is true because remember endothermic reactions, the delta H is positive and negative was for exothermic. So B is correct. So question 9, methane reacts with oxygen in a combustion reaction to produce carbon dioxide and water. This reaction is exothermic and the molar heat of combustion is minus 890 kilojoules per mole. Write a balanced equation for the combustion of methane and include the enthalpy change. So what's important here is that we need to write the chemical equation and then we also need to include this number here somewhere. So what we would do first is we know it's methane, so meth is 1 carbon. So methane has CH4 and methane is always a gas at room temperature and that means we need to put a G in there to say it's a gas. We also it says reacts with oxygen. Oxygen is O2 and it's also a gas. And when we react them together with the heat, a little spark, we can combust it and it says that we get carbon dioxide, which is CO2, remember? CO2 is a gas at room temperature, and water, H2O. And it's also a gas. So next we always have to make sure it's a balanced equation. So what do we do? First we count how many carbons we have on this side, 1. And we have 1 here, so that's fine. The hydrogens, we have 4 here. and then here we only have 2. So that means we've lost 2. We need to put in 2 on this side, so we put a 2 here. So now we have 4 hydrogens. Oxygen, we have 2 on this side, we have 2 here, plus another 1 times 2 gives us 4. So what do we have to do? We're missing 2 now on the left hand side. We put a 2 here, 2 times 2 gives us 4. So now we have a balanced equation. So just make sure you always double check it, because sometimes you add 1 on this side and 1 on this side and you forget. So 1 carbon, 1 carbon. 4 hydrogens, 2 times 2 is 4 hydrogens. Then 2 times 2 oxygens, 4. 2 times 1 is 2, 4. So that's fine. Now we need to include the enthalpy change, so minus 890 kilojoules per mole. So in this equation it says it's a combustion reaction. Combustion means we're releasing energy. So we're releasing 890 kilojoules per mole into the surroundings. So that means if we put it on this side, we're taking in the energy. So we're taking in this amount of energy to get this. So it's not what we're doing. We're not doing an endothermic reaction. We're doing an exothermic reaction. So that means this plus this. When we combust it, we're releasing energy. We're releasing another 890 kilojoules here per mole. And we only have 1 mole of methane here. So that's fine. So just to summarize, what we can do here is that we have our equation plus the energy on this side, releasing it. Or we can write it like this. So the chemical equation, and then we say on the side here, the change in enthalpy was minus 890 kilojoules per mole. We have to make sure we put the minus because it's exothermic. If we had it as a positive, it will say it's an endothermic reaction. So just make sure you put minus in there. Question 10. For the combustion of magnesium, state whether the process will be exothermic or endothermic. So this one is exothermic, obviously, because we said it was combustion of magnesium. So it's producing heat. Indicate whether the reactants or products have the higher enthalpy. So remember, in exothermic reactions where the reactants are lower than the products, so the reactants have the higher enthalpy. Identify whether heat will be absorbed or released into the surroundings. Exothermic reactions release heat, remember, because they feel hot. So it's released into the surroundings. So what we were doing today was looking at exothermic and endothermic reactions. Just remember that exothermic reactions release heat and therefore has a delta H of a negative number. And the endothermic reactions are the opposite. They absorb heat and therefore the delta H is positive.